Being able to estimate is really quite important in physics and engineering. Knowing roughly how much weight there's going to be, what the temperature is that you're expecting, roughly getting a ballpark answer for what your calculation should be. All these things are really, really important, and you should be using them every single time you do a question. So what we're going to do is look at a little process that gives you an idea of things that you can estimate. So one of the challenges that you could do is are known as Fermi tasks. And I know students who've been asked this at interviews. For example, how many ping pong balls would it take to fill a double-decker bus? And it's about that logic of using estimation to give you rough values. How many bananas would fit around the world? That kind of thing. So what we're going to do today is a little practical, quick demo practical to basically try to estimate the size of a molecule, okay, by measurement. Work out using a rough back of the envelope process, and that's generally what we mean by estimation, not guess, but actually calculate something out using approximate values. So the aim is I'm going to get you to, or we are together going to try and estimate roughly the molecules in this oil. Okay, so you can't do it without using either really high-tech stuff or using very advanced microscopy. However, what you can do is get a pretty good estimation for it. So the process is this. I'm going to use oil because it has certain principal characteristics. It floats really well on water. If you put it on water, it breaks the surface tension, and so what you'll find is that the water will spread out, or the oil will spread out on the top of the water, and it will form a measurable film on top. The idea is, by working out a drip of oil, putting that drip of oil, by using a calculation from based on the measurements of the drop, is that we're going to put it on the oil, and when it spreads out, we're going to assume that entire volume of oil has spread out into a flat disc. And the flat disc will be circular. It tends to be how it works out anyway, naturally, and it's going to be certain thickness. And we can say that that thickness, rather like trying to pile up marbles, tends to be about 1 molecule thick, maybe 2, but you know, it gives you a rough ballpark figure. So yeah, you try stacking them up, they're going to roll and spread outwards until they're at the lowest level they can get. So with the calculations on your data sheet, you know the volumes of these. You know for a disc, then it's the surface area multiplied by the length. In this case, let's call it h. And we know the volume of the sphere, which is 4/3 pi r cubed. So we're going to do some math on that. I'll have a close-up so you can see what's going on, and so we're going to break this video up a little. So here you can see our oil drop. I've got captured on a little bit of wire. By holding that against there, we can get a rough scale. So if I hold that still, to me that looks like a diameter of 2 millimeters, slightly under. So let's say, yeah, it's definitely over 1.5, but it's less than 2. So let's say 1.8 is only just below that, and that gives us our diameter of our oil drop. If we then obviously half that, then we'll get our radius. So we can do the first bit of the calculation. Here we've got the oil drop above the water, and if I drip it in, you can see it spread out and take all that paper that I had floating on the top. Sorry, wood pulp I had floating on the top. Now unfortunately it's not perfectly spherical, and it's still spreading out. So at the moment, I'm going to take the average of the two. That's 13.35. Centimeters, that is. I should quickly add. And that's giving us approximately, just to make sure I don't touch it, that's giving us around about just pretty much dead on 5 centimeters. So 50 and 133.5. So if we do the maths, we had a radius of droplet of 1.8 millimeters. It's gone to a flat disc. The disc wasn't circular, so I'm going to take the minimum and the maximum diameter and then average them, which gives me 91.7, which gives me an average radius of 45.88. We could round that up a bit, but let's stick with that a second. So in terms of mathematics, I've got my volume of the sphere, which is 4/3 pi r cubed. I've got my area and depth of my cylinder, which is pi r squared, different r, big R, times h. They've obviously both got pi in, so I can ignore that. So with the values we got, 4/3 1.8 cubed, 45.88 squared times h, which means that h equals all of that divided by that squared, which gives me 3.69 times 10 to the minus 3 millimeters, because all those dimensions are in millimeters. So basically that's approximately 4 micrometers. Okay, and that gives me the scale approximately of a molecule in the oil, which, if you think about it, is not too bad. You know, it gives me a rough ballpark. It's slightly smaller than that, but again, oils are polymers, so you know, the length can vary a little bit depending on the purity of the oil. So that's a pretty good way of estimating something that is so small you can't do it, and it's about using the right kind of plan to come up with your experiment that's going to work. Okay, and in this case, knowing the properties of oil and its ability to spread out. Brilliant. So here's my bowl of water, and I've got a little bit of wood floating on the top so that you can see the movement. And if I drop the oil in very quickly there, what you'll see is, particularly if I can pop it, is that when the bubble breaks, it will spread itself out, and it's not doing it. We've already lost the surface tension, haven't we?